Okay, we're going to do some examples with Bernoulli's here. And we did all the conceptual stuff on the PowerPoint, so now we need to copy Bernoulli's equation from our AP equations page. So do you guys have that? Let's take that out so you know where to find it. Bernoulli's equation, for some reason we call the princess of all physics equations. I don't know why. It happened one time and then it just stuck. Okay, so let's write it down. It says this. It says pressure 1, and it's really long, so you need a lot of space, plus rho g y1 plus 1/2 rho v1 squared is equal to pressure 2 plus rho g y2 plus 1/2 rho v2 squared. Okay, now that looks super intimidating to some people. What are all of these things, when you break down the units, what are they all measured in? When you add two things, what do they have to be, what has to be true about the units? Same. Okay, so what's pressure measured in?
Pascals.
Pascals. So what's that come out to?
Pascals.
And what's that come out to?
Pascals.
Pascals. Okay, so it's basically saying, okay, that our pressure for our fluid can come in three different ways. Okay? One of those ways right here is from a height difference. Okay? And you guys already know, how do you calculate the pressure at the bottom of a lake? Rho GH, right? Okay, this is the same thing. Look, rho G, and then instead of H, we got Y. Okay, and then there's also the velocity component. Doesn't the speed of the fluid change what's happening to the pressure? Okay, we've just added. So this part right here, this is what you already know. Okay, this can be the pressure behind the fluid, like the atmosphere, right? This can be from a height difference. So this is fluid statics, and then this right here is the new stuff. This is fluid dynamics. Okay, now later I'll show you where this equation comes from. Okay, but we're not going to do the proof right now. Okay, so let's do an example problem. Water circulates throughout a house in a hot water heating system. If the water is pumped at a speed of 0.5, is what that is. Is yours hole punched out? Through a 4 centimeter diameter pipe in the basement under a pressure of 3 atm. What will be the flow speed and pressure in a 2.6 centimeter diameter pipe on the second floor? Okay, so let's draw a very simple diagram. We've got a pipe, and it's going to go up here to the second floor. Down here, the pipe is one size, but then upstairs, there must be some kind of reduction fitting because the pipe gets smaller. Okay, now here's the deal with Bernoulli's principle. It always deals with a changing situation, a point 1 and a point 2. And isn't that how continuity works as well? For the principle of continuity, don't we have a set of values for part 1 and then part 2? Okay, so when you make these diagrams, you always need to label a side 1 and a side 2. So let's make the basement 1, and let's make the upstairs 2. Alright, and the nice thing about Bernoulli's principle is something always cancels. Okay, you actually never use this equation with all 6 terms. One of them always cancels, and sometimes more than one of them. Okay, so let's list what we know. Down here, We've got our speed, and that is 0.5. So we're going to put velocity 1 equals 0.5 meters per second. And then we've got the diameter. Let's go ahead and convert it to meters and say 0.04 meters. And then what else do we know? We know the pressure. So pressure P1 is equal to 3 atm. Alright, then we want the flow speed and pressure up here. Okay, so this diameter is 2.6, or let's put 0.026. And then we don't know what the flow speed is, and we don't know what the pressure is. Oh, thank you. Okay, meters. Alright, so can we solve this equation with two missing variables over here? No, we can't do it. Okay, so we're going to have to do something else first to get one of the missing variables. What's that going to be? Okay, it's not rho GH. We can't do rho GH because now we have moving fluids. It's more complicated. Oh yeah, we're going to do continuity. Okay, so I'm going to block off a little space right here. And we'll do continuity. And we're going to say A1 V1 equals A2 V2. And let's just rearrange it for V2. Okay, this is 2 up here. So V2 is equal to A1 V1 over A2. Alright, and now we just have to do number crunching. So area 1, we're going to do pi r squared. So pi, that's the cross-sectional area of this pipe. That's A1 right there. This is A2 right there. So pi, and then our radius is 0.02. Pi r squared times our velocity. Okay, V1 is a half, so I'm going to put a 0.5 right there. And then we're going to divide by another pi r squared. And down here, or up here, that's going to be 0.013. Square it. Okay, pi cancels. Go away, pi. Alright, and now we can just do the math. Okay, so punch it in real quick. Let's see what we get. So I got 1.2 meters per second. Do you guys agree?
Yes.
All right. So now that's this. We did continuity to get that speed, and now we can solve Bernoulli's equation. Okay, which looks kind of intimidating, but it's just algebra. Okay, you just have to put the numbers in the right places. Okay, so we want pressure, we want this. We want P2. Let's go through and look at each term. Down here at the bottom, do we have a pressure? Yes, what is it? 3 atm. We're going to keep that term. Okay, rho gy. Notice there's a rho gy on each side. Remember when we did potential energy last year?
Yes.
Okay, isn't there always a 0 point and then some point above 0? That's what's going on here. What point are we going to make 0? 1 or 2? 1. 1 is 0. So this term is going to 0 out because y1 is going to be 0. So we are saying y2 is equal to what? 5. So this term over here is going to stay. All right, now, do we have a velocity down here? Do we have a velocity up here? Both of these terms are going to stay. Okay, and this is the equation we're left over with. So that's what we're going to actually use. We don't need to rewrite it. Okay, let's just start plugging in numbers. You can rearrange it first if you want to, but Bernoulli's equation is so long. I usually just plug in my numbers and then solve for the missing variable. So I'm going to do that here. Pressure 1, 3 atmospheres is 3 times 10 to the 5th in pascals. Okay, this is P1. That term zeroed out, so I'm going to add that to 1/2 of 1,000 times V1 squared. Okay, so down here I've got 0.5 squared. Okay, then I've got this side. So P2 is what I want to find. I'll leave that as P2. Rho gy is 1,000 times a 9.8 times 5. Okay, then I'm running out of room. So I'm just going to put it down here. 1/2, another 1,000, V2 squared. Okay, we found V2 right here. It's 1.2. And we're going to square it. Okay, did I mess anything up? Okay, I think it's good to go. Alright, now it's just some number crunching. So let's throw that into our calculators and see what we get. Alright, you guys punching this in? I'm going to write an intermediate step. Okay, so I added those two and got that equals P2 plus, and then all of this when multiplied and added together should get 49,720. And then we just need to subtract and get P2. $250,405. That's pascals. Okay, let's round that for sig figs. And we get 2.5 times 10 to the 5th pascals. Okay, so notice we had 3 atmospheres. Now we have 2.5 atmospheres. Okay, so the pressure in this stream right here is going to be 2.5 atmospheres. Okay, and that's the whole problem.